Hello, welcome back to the lecture series on theory of semigroups. We are doing Rees theorem. In the previous theorem, we have discussed the following lemma. So I will state this lemma again here. And the lemma is the following. This is our lemma that we have done in our previous lecture. That this S is regular. S is regular and has exactly 2 D classes and has exactly 2 D classes namely 0 class which contains only one element, that is 0, and second is S minus 0, which we have denoted by T. And again we have seen that in the same lemma, if A, B, they are in D class, then obviously either AB is equal to 0, because this product is in S, but S is the union of 2 D classes. One is containing only this 0 element and second is S minus 0. So that product, it is either 0 or it is in the D class D. Okay. So it states that if A and B in D, then either AB equal to 0, then either AB is equal to 0, or if AB is not equal to 0, then we have the following. Then this AB belongs to the following H class, which is RA intersection LB. RA intersection LB. And in the later case holds, then LA intersection RB contains an idempotent. Okay. So the later case occurs if and only if, okay, the later case means that this AB is here RA intersection LB. This occurs only if, or it is actually if and only if this later case occurs if and only if the H class LA intersection RB contains an idempotent. So this we have seen in our previous lecture. Okay. So we have done the proof of this result in our previous theorem. Now let's come to the proof of the theorem again. So let H be an H class of S. Suppose we take any H class. Let H be an H class. Let H be an H class of S. H class of S. Okay, contained in a D class, containing in the D class D. Containing in the D class D. Okay, containing the D class D, because each D class is actually union of L classes, and H class is contained in L class. Okay, so this H class, it must be contained in some D class. So let's take that D class is D, which is equal to S minus 0, which we have already seen in the previous lemma. This is your S minus 0. Right, and let's take any two elements, and let these two elements A, B belongs to H. So that means they are in D. Then in the previous lemma, either AB equal to 0 or the product belongs to RA intersection LB. That we have done in the previous theorem. Then either AB belongs to, then either AB belongs to, then either AB belongs to, this AB belongs to RA intersection LB, RA intersection LB, AB belongs to RA intersection LB, or AB equals to 0, or AB equal to 0, or AB is equal to 0. And in the former case we have this H is a group by Green's theorem, and in the former case means that this AB belongs to RA intersection LB. In the former case this LA intersection RB contains an idempotent. LA intersection RB contains an idempotent, in the former case this one contains an idempotent. So but here you note one thing, that AB belongs to RA intersection LB. This is your H class, okay, and this is same as LA intersection RB, and this contains an idempotent, okay. So in the former case in the former case LA intersection RB, this is again equal to H. This contains an idempotent, and hence by Green's lemma, if H class contains an idempotent, then this must be a group. By Green's lemma, the statement the lemma number is, by Green's lemma, it's theorem 2.2.5. Theorem 2.2.5. It's Green's theorem, not Green's lemma, okay. This is Green's theorem 2.2.5. This H is a group. This H is a group. So this is the first case, and in the second case we will see that H class is always equal to 0, okay, that we'll see. So in this way we are actually proving that every H class in a D class is either a 0 H class or it's a group. That we are going to prove actually, okay. So this H is a group in this case, and in the later case we show that H square is equal to 0. हम ये प्रूव करेंगे, this is equal to 0. So for this we take any two elements of H and we will show that their product is equal to 0. So let's C and D belongs to H. We show that CD is equal to 0. We show that the product is equal to, where it is given that AB is equal to 0, okay. CD is equal to 0. Now since CD they are H related, so we can find two elements there exist. So choose X comma Y in S, in our semigroup S, such that C is equal to XA, because this C is H related to D, okay, and H is actually the intersection of L and R, so that means C is L related to D as well as R related to D. So from L related to D we can find X such that C is equal to X. This X on the left side, and C is also R related to D, so I can find Y such that this D is equal to BY. It's here D, sorry, C and D, it's D here, and here D is equal to CY. Sorry, D is equal to BY. C is equal to XA. Okay, A and B are also in H, so they are also H related. So it means that C is actually H related to A. So sorry. Now this is also given here. This A and B, they are in H such that AB is equal to 0. This is given, okay. A and B are also H related, and H is an equivalence relation. C and D, they are also H related. And now H is an equivalence relation. It means that A is H related to C and D is H related to T. So we can choose X such that C is equal to XA, because C and A, they are H related. It means that they are also L related. So we can find X, which is on left hand side, such that C is equal to XA. And for D is equal to BY. D is equal to BY because D and B, they are also H related, hence they are R related. So we can find Y, which is on the right hand side. So this can be done. We can find more elements actually. So in particular, we can find these two elements X and Y with this property, right? So now we can see the product CD. Now what CD? C is equal to XA and D is equal to BY, but AB is equal to 0 in this case, so it's equal to 0. So thus H square is equal to 0. Thus H square is equal to, because product of any two elements of H is equal to 0 if AB is equal to 0. Okay. So if in H class product of two elements is equal to 0, then product of any two elements is equal to 0. So in other words, we can say this H is actually this it's like null, because product of any two elements is equal to 0. Yeah. So we may summarize this like we say that the H class within D are as either group H class or a 0 H class. So thus every H class, thus every H class within D, जो आपके पास D क्लास है, दो ही D क्लास आपके पास है, एक तो D है, सेकंड इज 0. within D, every H class within D class are either they are either group H classes, जो H क्लास या तो ग्रुप होगा, ग्रुप H classes, or must be 0 H class, 0 H class. Okay, so any H class is either group H class or 0 H class. So actually what we have to show, actually we have to see that this S, this 0 completely semigroup is isomorphic to Rees matrix. Okay, for this we have to construct a group and we have to construct two index sets I and lambda, right? So we are not ready to construct that 0 complete semigroup. Okay, we are not ready. So for this we must construct these I and lambda, then we must construct the group, right? So we are now ready to prove that this our S is isomorphic to that semigroup. There is a group H and the index set I and lambda such that this S is isomorphic to M naught I G lambda, that we call the Rees matrix group. Okay, Rees matrix semigroup. Okay, for this let's take a set of all non-zero R classes and let's note that set by capital I. So now we come back to the proof of the theorem. Now we return to the proof of the theorem. Now we return to the proof of the theorem. Okay, so let I denotes the set of all, let I denotes the set of all non-zero R classes, non-zero R classes, and lambda denotes the set of all non-zero L classes, non-zero L classes. Okay, so we may treat these, we may treat this I and lambda as the index sets. We may treat them as index sets, and we write our R class then, and write R classes as Ri, where I is in capital I, and the L classes as, and the L classes as L lambda, such that where this lambda belongs to the capital lambda. So they are actually non-zero L classes and R classes. The H class is denoted by the H class. The H class, which is actually the intersection of L class and R class, the H class, which is equal to Ri intersection, which is equal to Ri intersection L lambda. Okay, if either this contains only 0, either the product is equal to 0, then H class is 0 obviously, and the product is not equal to 0, then this is actually the group. So this we denote by H I lambda. So these are just notations. Okay, by indexing these H class and R classes by I and lambda, so we may use these notations. Each R class will be denoted by Ri, where I is in I, and each L class will be denoted by L lambda. It's not the fancy L here, L lambda, simple L lambda, where lambda belongs to the capital lambda. Then each H class will be equal to each H class, which is Ri intersection L lambda. We will denote it by Hi lambda. So since our D class is regular, since D is a regular D class, since D is a regular D class, since D is a regular D class, why it's a regular D class? Because it has at least one non-zero, because it has idempotent, and every idempotent is a regular element. So because our semigroup is a zero completely simple semigroup, so zero completely means that it has a minimal non-zero idempotent. So non-zero means that that idempotent must belong to D, because D is equal to S minus 0. So whenever any D class contains a regular element, then each element of D class is regular. Okay, so since this is D, it contains the idempotent, non-zero idempotent, which is a regular element, so that means this D is regular. It's a regular D class. So it follows by proposition 2.3.2. It follows by, actually we are using here Green's lemmas, okay, all the Green's lemma. It follows by proposition 2.3.2 that each Ri contains, that each Ri means each R class, each Ri contains an idempotent containing an idempotent, that means contains, because R class is actually the union of it contains H class, okay, but each R class contains idempotent, so that means this Ri, which is equal to the union of H classes, so that means at least one H class contains idempotent. So the H class which contains an idempotent, that H class is actually a group, because any H class which contains idempotent is a group. Okay, so this by that lemma, Ri contains at least one group H class. Ri contains at least Ri contains at least one group H class. One group H class. At least one group H class. This Ri, it contains at least one group H class. So equally one group H class, let's denote that by H I lambda. Okay. Equally each L lambda contains each L lambda class, each L lambda which is an L class contains at least one group H class, one group H class, because contains at least one idempotent, and therefore there is an H class which contains that idempotent, and hence that H class is a group actually. H class contains one group H class, So without loss of generality, we may assume that there is an element without loss of generality. Without loss of generality, we may assume that there is an element. Say 1. It's not. You can denote it by any index. Okay. So we denote it by 1. It hardly matters. Which is in I intersection. We take the same index actually. I intersection lambda, such that this H11 is a group. It's a group H class. Okay. It's a group H class. So denote the identity of this H11 by E. Denote the identity of H11 by E. So let's denote this identity by E. So there are any number of groups, okay, H classes which are groups actually, but we know that by certain result that each H class group, if any two H class groups, they are actually isomorphic. So note that choice of one particular group H class does not affect the. Since we know the since we write this like this, since by proposition, okay, you write that proposition actually by proposition 2.3.6, since by proposition 2.3.6, okay, by proposition 2.3.6, by this proposition all group H classes in a D class D, all group H classes in a D class D, are isomorphic. So if they are isomorphic, therefore we can choose any one of them, okay, because they are isomorphic. Therefore one particular choice of group H class does not affect. Therefore one particular choice of group H class does not does not affect the conclusion of the theorem. Conclusion of the theorem. It will not affect that. So we will see that this group जो हमने ऊपर लिखा है H11, this group will turn out to be the group which is in actually Rees matrix semigroup. So we will see that the group H11, we will see that the group H11, we'll see that the group H11 will turn out to be a group which is in the Rees matrix, which is in the Rees matrix semigroup. एक्चुअली हमें प्रूव करना है कि दिस एस इज आइसोमॉर्फिक टू रीज मैट्रिक्स सेमी ग्रुप, और उस रीज मैट्रिक्स सेमी ग्रुप में एक ग्रुप होता है जो आपने इसकी कंस्ट्रक्शन ऑलरेडी देखी है. तो हम कहेंगे कि हम प्रूव करेंगे वो जो ग्रुप वहां पर है रीज मैट्रिक्स सेमी ग्रुप में, वो हमारा H11 है जो हमने यहाँ पर लिया है. ओके, तो दिस इज एक्चुअली द ग्रुप. So now for each I and lambda, we choose an element Ri. Now for each I and lambda in capital lambda, we choose an element Ri. We choose an element Ri which is in Hi1, and we choose an element Q lambda which is in H1 lambda. Now since we can see that since R1 Ri, it's L related to E. It's L related to E. Okay, R1, sorry, not Ri in general. Let's write here R1, not what I'm writing. Since this R1, it belongs to H11, so that is this R1 is H11, it contains the identity E, so that R1 is L related to E, because it is both L as well as R related to E. It's actually H related to E, as both R1 and E, they belong to this H class, H11. So we have a proposition, we have by proposition 2.3.3 that from this proposition we have RIE is equal to RI. RIE is equal to RI. So because this idempotent it acts as right identity for this L class. Okay, RIE actually it's here RI. It's RI here. Okay, it's RI because these groups are all actually isomorphic. E belongs to Hi1 also. They're all isomorphic. So this hardly matters. It's E is in every H class actually. So in fact, since it is true for each I and lambda, we can choose I equal to 1 and lambda equal to 1. then we can write this R1 is L related to E. So hence by Green's lemma now, hence by Green's lemma, hence by Green's lemma, what's that lemma? That lemma number is 2.2.2. This is Green's lemma. It follows that this translation which maps xi to its left translation, it follows that the left translation x maps onto this Rix. This left translation, this is a left translation, maps H11 onto Hi1 in a 1-1 manner. That means that map is 1-1 in a 1-1 manner. Actually, in that lemma you have proved that the cardinality of H11 and Hi1 is same, so that's why there is via this map. Okay, so this map is actually a bijection in a 1-1 manner. Similarly we have this EQ lambda is equal to Q lambda. So this is actually it is the idempotent of L class as well as R class. So this acts as a left identity for R class. Okay, EQ lambda is equal to Q lambda. So therefore, again by Green's lemma, again by Green's lemma, which is lemma number 2.2.2, again by the Green's lemma, same Green's lemma 2.2.1, sorry. So because there are two Green's lemma, one is from left translation, second is from right translation. By Green's lemma, again by Green's lemma, the right translation, that the right translation which maps y to yq lambda. Okay, this translation it maps Hi1 onto Hi lambda in a 1-1 manner, in a 1-1 fashion, So therefore we can choose Ri and Q lambda. So by choosing, so once we are choosing these two elements, so therefore we have a unique expression. Thus we have a unique expression. Thus we have a unique, why unique actually? This is very important. Okay, there is a unique expression which is RIA then Q lambda. Actually, first we apply the left translation. This is a unique image, and this one is also the unique image. This one is under the right translation, this one is under the left translation. So the image is unique. That's why he is writing here. Thus, we have a unique expression actually. RIAQ lambda, while A is in H11. So first, you see, we have a bijection from H11 to Hi1, and second we have bijection from Hi1 to Hi lambda. So you can compose these two bijections. You will have a bijection from H11 to Hi lambda, and by that bijection you have a unique expression for any choice of Ri and Q lambda. You have a unique expression Ri A Q lambda, by A is in H11. So it is this is actually the image. This Ri A Q lambda, it's actually the image of A under that composition. So first you apply the first composition, which is x goes to y, which is x goes to Rix, and second is the y goes to Yq lambda. You apply these two compositions. You apply these two mappings, and let's compose these two mappings. You will get this composition which maps A onto Ri A Q lambda. So this is unique actually. So image, because image is unique under these mappings. So we have a unique expression for any choice of Ri and Q lambda. You have this unique expression for each element. For each element of each element of Hi lambda का कोई भी एलिमेंट आप लीजिए, आपको ये यूनिक एक्सप्रेशन मिल जाएगा, बिकॉज दैट मैप इज ऑल्सो ऑन टू. आप Hi lambda में कोई एलिमेंट लीजिए, यू मस्ट हैव a pre-image under that composition. And what's the pre-image? Pre-image is this. And this is also unique because the map is 1 as well as onto. So it's really interesting because first you have the bijection, you have this bijection first, which maps x onto which maps x onto Rx, and second is y, which maps y maps onto y, then Rq. So let's compose these two bijections. It will see, you will see that this x is a map which maps x onto Rix, Rq. Okay, these two, sorry, Q lambda is here. What I'm writing here, it's Q lambda. Okay, it's here Q lambda. Clear, it's Q lambda. Q lambda, and here it's Q lambda. Okay, it maps A onto this. So this map, this ये जो map आपने यहाँ लिखा है ना, x maps onto Rix Q lambda. This map is 1 1 onto. So it's a map from H11 to Hi lambda. You can see the composition. So this means that for any choice here, if you choose any, or for any choice of I lambda, you have Hi lambda which is H class, and for any element in this Hi lambda class, every element has this representation via this map. Okay, so every element has this representation, must be this representation. So there is some A such that A is equal to Ria. So for any element here, if you choose any element, say Z here, there must be A such that Z is equal to Ria Q lambda. So every element of Hi lambda has unique expression like this, Ria Q lambda. This is it. So once you have this representation, now you have this representation, and now since our S minus 0, our D, since our D which is equal to S minus 0, which the union of H classes which are non-zero H classes, and the one H class is 0 H class. So we are taking here non-zero H classes. It's intersection of these H class, Hi lambda, where I is in I, because you are taking non-zero, actually non-zero L class and R classes. I is in I, lambda is in lambda here. And since the union is disjoint, or union disjoint भी है, and since the union is disjoint, so we thus have a bijection. We thus have a bijection. We thus have a bijection phi from I cross H11 cross lambda to S. So that we actually need this bijection. We show that this S is isomorphic to this one. So we don't have defined it yet. We don't have defined the product on this in this set, so that it will be a semigroup. okay, and this S will be isomorphic to I cross H11 cross lambda. But we define a map, and with the help of this map we try to define operation on that set so that it will become a semigroup, and it will also be the morphism, isomorphism. This map will 1 1 onto the hai, that's there because of previous discussion. It's a bijective map, this map that we are going to define. So it's defined 5 from this. Here it's hi cross h11 cross lambda union 0. Okay, this is because it does not contain the 0 element, union 0, and S contains 0, union 0. Okay, union 0 to S. We define this by given by we have bijection which is given by this phi. This is I a lambda of phi maps this element onto I. It's not no, this is not here I, it's Ri a, then this is here that in the previous this q lambda. Okay, this element is in S, because since this S is union of H classes, and if you choose any element in H class I lambda, you must have this Ri, that we have discussed in our discussion in previous. So this as it's actually union of these Hi lambdas. Okay, तो अगर आप इसमें से कोई भी एलिमेंट चूज करोगे ना, वो किसी न किसी एच आई लैम्डा में होगा, और जो भी एलिमेंट एच आई लैम्डा में होता है, यू कैन फाइंड दिस आर आई एंड क्यू लैम्डा सच दैट दैट एलिमेंट इज इक्वल टू आर आई ए क्यू लैम्डा, एंड दिस इज इमेज ऑफ ए एक्चुअली. एंड नाउ यू कैन ट्राई टू एक्सटेंड दिस मैप ना. एक्चुअली आप H11 से लेकर वहां तक मैप डिफाइन करें, तो अब क्योंकि सारा एस आपको कवर करना है, दैट एस इज यूनियन ऑफ एच आई लैम्डा क्लासेस, तो आपको इसलिए ये दोनों इंडेक्स सेट इसमें लाने आई क्रॉस लैम्डा, सो दैट दिस एलिमेंट विल डिपेंड आल्सो ऑन ए एज वेल एज ऑन दीज टू इंडिसेस आई एंड लैम्डा. हाँ, अगर आपको एक ही एच क्लास लेना होगा तो उस केस में आपके पास H11 टू एच आई लैम्डा मैप थी, दैट वाज 1 1 ऑन टू. तो अब आपने आई क्रॉस H11 क्रॉस लैम्डा लिया, तो आपने इस तरह से इस मैप को डिफाइन किया. और इसका रीजन ये क्यों बाइजेक्शन है, बिकॉज दिस इज द डिसजॉइंट यूनियन. तो जब भी आप आई और लैम्डा को फिक्स करोगे, आपके पास एक एच आई लैम्डा होगा, और यहाँ पर कॉरस्पॉन्डिंग इंडेक्स आप लिख सकते हो ना. सपोज आपने आई भी 1 लिया और लैम्डा भी 1 लिया, तो उस केस में 1 क्रॉस H11 क्रॉस 1 से लेकर H11 तक मैप होगा. अगर आप आई आपने 2 लिया, लैम्डा आपने 2 लिया, तो यू विल हैव 2 क्रॉस H22 क्रॉस 2 H22. No, H11 is fixed here. Okay, H11 is fixed here. It does not depend on these indices. Okay, so this is the map. It is a bijection map, but you want isomorphism actually. You want isomorphism. तो isomorphism के लिए दोनों semi groups होने चाहिए. So you will define the product or the binary operation on this set I cross H11 cross lambda in a way that it will become a semi group, and this map will also be in isomorphism. तो आप इस तरह से इसमें प्रोडक्ट डिफाइन करोगे ताकि ये जो सेट है आई क्रॉस H11 क्रॉस लैम्डा, ये सेमी ग्रुप बन जाए, यूनियन 0, ये सेमी ग्रुप बन जाए. और सेमी ग्रुप ही नहीं, सिर्फ ये जो मैप जो आपने डिफाइन किया, ये आइसोमॉर्फिज्म बननी चाहिए. और ये प्रोडक्ट कैसा होना चाहिए, प्रोडक्ट वैसा ही होना चाहिए जो आपने ऑलरेडी कंस्ट्रक्शन में किया है. प्रोडक्ट को डिफाइन इसके लिए आई क्रॉस H11 क्रॉस लैम्डा के लिए. So now we are in the final stage. Actually, we want to prove that this map is an isomorphism. So we are now introduced. We try to define. We now define. We now define a multiplication. Define a multiplication on which set I cross H11 क्रॉस लैम्डा. हम इस पर मल्टीप्लिकेशन डिफाइन करेंगे, यूनियन 0, यूनियन 0, so that it will become a रीज मैट्रिक्स सेमी ग्रुप. एक तो ये रीज मैट्रिक्स सेमी ग्रुप बन जाएगा, रीज matrix semigroup. It will become a Rees matrix semigroup, and आइसोमॉर्फिक टू एस, एंड बाइजेक्शन तो है ही आपके पास, आइसोमॉर्फिक के लिए आपके पास मॉर्फिज्म चाहिए, आइसोमॉर्फिक टू एस, आइसोमॉर्फिक टू एस. So this forces us to define the multiplication as follows. So how do we do that multiplication? So but on the right hand side अगर आप देखोगे right hand side में प्रोडक्ट क्या होगा? So what's the multiplication on the right hand side? That's very important. That multiplication is very important. That multiplication is very important. How do we do that multiplication? So you are actually defining the multiplication of two elements of S. So the multiplication is simply a simple जो आपके पास S में multiplication already है. So let's try this for any this I K Ri, sorry. So Ri is an element of this R class, actually Ri A Q lambda and Rj B Q mu belongs to S. We have the product is this simple, it is because there is already defined a product. So this is equal to RJB Q mu. Okay, it's like this. So this is equal to Ri, then you write here A Q lambda Rj B, then Q mu. So at least you have this because both elements are in S. You have this. So it if we use the following notation, if we put this product, put not the whole product but this Q lambda Rj, Q lambda Rj is equal to P lambda G, P lambda G, P lambda G. Okay, so then by that we already discussed the product of two elements in this H class, actually in D class. It is again in the H class by lemma 3.2.7, which we already discussed. This product P lambda J, what's this? This is actually Q lambda Ri. Actually it's Q lambda Ri, Q lambda Rj, sorry. It belongs to, it's element A, it's element B. Okay, it's a product of two elements. It belongs to RQ lambda intersection LRI, and that's equal to H11. So by lemma this is equal to H11 if and only if the H class, because it is on the image side actually, if and only if this LQ lambda intersection this Ri is equal to Hi lambda. एक्चुअली ये जो है ना, ये इसकी इमेज है अंडर दैट पार्टीशन. और ये इस लेमा से क्यों फॉलो हो रहा है? क्योंकि यही लेमा कह रहा है कि ये इंटरसेक्शन में होगा. इस इंटरसेक्शन में, ओके। अब ये इंटरसेक्शन H11 होगा इफ एंड ओनली इफ अगर ये इंटरसेक्शन HI लैम्डा होगा, बिकॉज द इमेज ऑफ HI लैम्डा इज H11 एक्चुअली. दिस इज द रीजन. This is the reason because that composition, that left translation and right इनका जो composition होगा, that composition is a map from H11 to HI lambda. तो अगर ये element H11 में होगा, इसकी obviously इसकी जो image होगी ना वो HI lambda में होगी. That's straightforward. So this is true H11. So this element is in H11 if and only if this product, this intersection is HI lambda. HI lambda. And this HI lambda, it contains an idempotent. ये तो तभी होगा ना जब ये आइडेम्पोटेंट को कंटेन करे. ये जो प्रोडक्ट होगा ये इंटरसेक्शन में होगा इफ एंड ओनली इफ दिस कंटेन्स एन आइडेम्पोटेंट. दैट इज इफ एंड ओनली इफ HI lambda is a group. This is a group. So if it contains an idempotent, if and only if HI lambda is a group. So otherwise P lambda you take 0, उस केस में 0 होगा. Otherwise reason वही actually previous discussion है. Otherwise P lambda I is equal to 0. Otherwise the intersection is actually 0 है. तो H क्लास या तो 0 होगा या ग्रुप होगा. Reason is the same. So let's define this matrix. So define P equal to P lambda I. Okay, P lambda I. Okay, P is subscript lambda I. Okay, P equal to P lambda I. This then P is a regular matrix. Then P is a regular matrix क्योंकि इसके जो rows हो गए ना that are with respect to lambda are corresponding to the, I think they are L class or R class, and we know that these L class they are non-zero classes. They are non-zero classes, so that means ये जो L class आपके पास होगा इसमें कम से कम एक non-zero entry तो होगी. So that means each row contains at least one non-zero entry, and each column is also containing at least one non-zero entry, which means that this P is a regular matrix. P is a regular matrix because lambda and I. Okay, so this capital lambda, it is the index set, it is the class of all non-zero L classes, and capital I is the class of all non-zero R classes. Okay, non-zero means not equal to 0. Okay, so the entries of the matrices, they are actually coming from the group H. Okay, H0, H11 and 0. So these P lambda, they are either equal to 0 or it's equal to the idempotent that we already discussed. This product P lambda I, it is in H11 or it's equal to 0. So in case this HI lambda contains an idempotent, so then this is the intersection actually in that case, and in the second case it is either equal to 0. So the entries of this matrix P, it's P lambda I. So P lambda I is either equal to 0 or in this class H11. P lambda I, it's in the class, it's in this group H11. So that means the entries of the matrix P, they are from H11 union 0 because they are either equal to 0 or belongs to H11. So hence the entries of P, thus the entries of P are the members of, thus the entries of P are the members of H11 0. So H11 0 means the zeros adjoined to H11 group. It's now 0 group. H11 union 0. Okay, so in this way we have defined the product in that cross product. So now it's so with the help of this product you are trying to so what's now product actually. So you have seen that you have you have actually this I a lambda phi and j b lambda phi. This should be equal to what? This should be equal to I a lambda, then j b, it's here mu not lambda, okay, j b mu of 5. But the product should be equal to what? Should be equal to I a lambda times j b mu, which you have seen that it's equal to I a then p lambda j and mu, p lambda j mu, and then p lambda j b, okay, p lambda j b then mu. So this should be like this, okay. So but this one you can see, this one, this is actually equal to I p, sorry, what I'm doing, and this is equal to I, the first entry, and the second entry is a p lambda j b then mu of 5. So that means the product of these two elements I a lambda j b mu is equal to I a p lambda j mu, and with respect to this product it's a semigroup. It's that Riemann matrix semigroup, okay, and this map will become an isomorphism with respect to this product. So hence our S is isomorphic to, it's isomorphic to which group? It's isomorphic to Riemann matrix group M0. And what are the parameters in this Riemann matrix semigroup? The first, the group is the H11, and the index it's I lambda, and this is the matrix P, which is a regular matrix.